Hi y'all, my name is Mira Kuntawala and this is my lab for Physics 2211 Choose Your Adventure. So for my Choose My Adventure lab, I chose to do something on collisions, which is one of the last topics that we've covered in this course. And the reason I chose this is because collisions are pretty common, as we know, with things like car accidents. And for me, it was just something that I really wanted to gain a better understanding of because it has a real world application. So I went about this lab by observing the motion of a model of a collision using a moving object that hits a stationary object and sticks together. And then I wanted to replicate that motion using a VPython model and then use the data that I gathered from both of those to help myself analyze the changes in momentum and the changes in energy of the systems. The results of this lab were that the computational model well predicted the motion of the experimental model, and that momentum was conserved, and that a change in energy was noted, which I will explain later. The two main physics principles that were utilized in this lab were A, the momentum principle, which states that the change in momentum is equal to the net force times the change in time. But during a collision, the net force is zero. So that would make the change in momentum zero, thus conserving momentum. The second principle was the energy principle, which states that the change in internal energy is equal to Q minus W, which is the heat in the system subtracted by the work that's done by the system. For inelastic collisions, the final kinetic energy is not equal to the initial kinetic energy. So there's a change in internal energy that is not equal to zero. The initial conditions of the lab were that there were two cars. The red car, which was stationary until the collision began, and then after the collision, its speed was negative 0.577 meters per second, and its initial position was shown as there. The blue car is the car that's moving at a constant speed of negative 1.09 meters per second until the collision. And then after the collision, when it's combined with the red car, they move together at a speed of negative 0.545. And its position is shown below as well. So in Tracker, I uploaded a video off YouTube that helps demonstrate this collision. I made my axes here in the left-hand corner, the calibration stick, which is equal to 1 meter, and then use the point mass track to track the mass, the center of mass of the red car, the blue car, and then the combined after the collision. The reason that my speeds are all negative is because my system is moving in the negative x direction. Here we can watch the tracker video to see this change. So as you can see here, I have a graph of my position over time for the two cars once they're collided. And if we look at, for instance, the position over time graph for the red car, the position stays stationary and then decreases down because it's moving in the negative x direction. And same thing for car B, only it's more constant because the car is in motion the entire time. So using the data points that we received in Tracker, I created two CSV files, one for the red car and one for the blue car. These CSV files help import the data from Tracker to help us create the model that we need from VPython. So after I imported those two files, I put the initial positions for both the red car and the blue car, along with their masses, and then the initial velocities. And the initial velocities I just found from the Tracker data points by just doing the change in x over the change in time. Then I define my variables here below, again restating the initial positions and velocities, and then here I changed the energy principles to help model what I need for the red car and the blue car. Below that is the time loop that helps update the position using Newton's second law, and then also the total change in momentum and what it's equal to. And then below here, calculated my final momentum, what it should be, the final kinetic energy, and then the print statement. So now when you run the code, you see that the blue ball hits the red ball and then they move together until they stop. And that's very representative of the video that we just saw in Tracker. In addition, if we are to look at the print statement, we see here that the change in momentum is zero, which makes sense. And then below here is the change in energy, which is 0.0752. And this change in energy makes sense because our model does not calculate for any friction that the system actually undergoes. So the real system experiences friction, but the computational model is not able to calculate that. And so that makes sense that there's a disparity in the change of energy between what we have in VPython and what we observed in the video. Lastly, I want to discuss what makes this model maximally inelastic, and that is that the two cars are stuck together after the collision, and that's the definition of something being maximally elastic. So this is my lab on Choose Your Adventure, and I hope you enjoyed it.